So, so we'll actually continue with the lecture, and since we have got some time free, so we will consider lecture 12 now. So today we take two classes, two periods, lecture 11 and lecture 12. So we'll continue with what we are discussing. So monatomic gas is over, internal energy, you have got the answer, 3 by 2 RT or 3 by 2 KT. So diatomic, let us complete this. Ideal gas, still ideal gas, okay. So remove all these things. Diatomic. Like hydrogen, oxygen, nitrogen. So again you tell me, so N is 2, how will you call this? So N is 2. Then degrees of freedom, DOF, this is 3N, this is not phase rule degree of freedom, a different kind, 6. So 6 you have to distribute, but since kinetic, since we consider they are behaving ideally, it's ideal gas. So 6 kinetic mode. What is the 6? I give you this. 3 modes of translation. 3 modes of translation. 3 translation. 2 rotations. Rotational. 1 vibration. Did I tell you the types of kinetic energy? These 3 I have mentioned. Thank you, thank you. Translation, rotation, vibration. Okay, each is equipped with half kT. So half kT translation again 3 direction. You know, translation is 3 direction. So 3 into what is the energy, corresponding energy? 3 into half kT per molecule. When I write K means molecule. 3 by 2 kT. 2 rotation, likewise half kT is kT, and vibration typically negligible, small, negligible. For light molecules. Particularly for light molecules like e.g. like hydrogen. Heavy molecules may have some vibration. I will discuss this part. Hey, you came and start. 1 vibration. Now, what is the total? Now, I will show you how it is happening. This is 1 molecule, hydrogen, say. 2 molecules. Now, see independently this. I am very sorry. 1 hydrogen atom, okay. Hydrogen atom. Hydrogen atom. Sorry, I should not, okay. Hydrogen atoms, okay, 2 hydrogen atoms. Now you follow each atom, okay. So what I said this here, diatomic 2 atoms, okay, very good. 2 3 and 2. Okay. So what is happening here? Sorry. Previous one was monatomic molecule. 1 atom, 1 molecule, okay. So this is, what is this? 1. And this is also X direction. This all X. This is Y. Okay. So no okay. This is 1 direction. Another is, tell me, this direction. Another is, and then this is dotted, and this is still another one. 3 direction. This similarly it will get also. It will have. I want to explain this 3 translation and 2 rotation, 1 vibration. So this atom also likewise this and dotted. Here also give a dotted also other side, dotted other side. Okay, so this is over 6. It's 3 actually, 3 with this, and similarly with this 3. Then you give this. So this. Okay, maybe I'll do this. Then give this dotted. Then give this direction, and this is dotted. 6 6. Okay, now follow. When these two atoms, this is a hydrogen molecule, these two atoms are moving in the same direction, either this or this will constitute one translation. Constitute one which direction? Suppose this is the x direction. Either both are same direction. So one, the molecule itself has 1, or this the same. So 1. This will you get 1. Similarly, suppose this is moving this direction, this is also moving this direction, or this atom is moving in this direction. Suppose y direction, or call it what, z direction. Z. This is also this direction. So again 1, 2. Third is what? Tell me. This is the direction. This is also same direction. 1, or this is in the reverse direction. This is also in the reverse direction. Means same direction. So these are the same. Remember, these and these do not constitute 2 direction. Then you 6 dimension. This space is then 6 dimension. If it is x, then the downstairs, okay, this will be another minus x is x, so another dimension. No, this is same. X, this or that. Okay. Similarly, y or happy. So 3 is explained. 3 translation. Now, suppose this is moving. Now consider this. This is moving this direction, but other atom is moving this direction. Sorry. This direction. What will happen? Not in the same direction. This is this direction. Say plus x. This is minus x. Then what will happen? This make a moment and couple, and that will cause rotation. So this is the cause of the rotation. Similarly, see here. This is this direction. The minus y. This is plus y. This atom plus y. This is minus y. Again, what will happen? A moment will be developed and a rotation will result. So how many? 2. So I have written 2. But what happens to this? You see, follow this in this direction. This is in this direction, and this is in this direction. This direction. This cannot form a couple moment. Okay. So this is what? Vibration. So also say this way. Consider this is this way, moving this way. The other one moving the other way. So vibration. You know vibration like this. So 1 vibration. Now I give you, this is okay. Vibration is typically small. This is a quantized vibrational energy. Note, vibrational energy is highly quantized. You know there is quantized. You know what is quantized? There is actually forbidden energy gap between the levels. So what is the value? If you ask me this U vibration, I give you this for diatomic. Diatomic is what I am giving a value. This is actually the oscillator energy. You know that is actually Planck's theory. He considers actually the oscillator. So vibration. So is what? H nu e to the power h nu by kt minus, this is the expression. Remember this. H nu, or nu is the frequency of vibration. Nu is the frequency of vibration. H is Planck's constant. And K, you know, Boltzmann constant, T is the temperature, you know. So this is the expression. Now as I told you here, at low temperature, at low temperature, also at low temperature. As low temperature, when it is low, okay, this is what happens. Low temperature means this is large. Large means numerator denominator is large, so it will be small. Or this is low and frequency of vibration is large. Because light molecules have high frequency of vibration that are compared to heavy molecule like bromine and iodine. Bromine, iodine. So anyway, we have got this. This value will be for light molecule. This will be 0. So U vibration for light molecules, high frequency of vibration for light molecules with high, that is high frequency of vibration. And at low temperature. Room temperature is low temperature. So this is the result that we discussed. So total is how much? Total U is how much? So U total diatomic, how much you are getting? Tell me. Okay, 3/2 kT plus kT is what? Per K means molecule. And you can write what? 5/2. Okay. Triatomic similarly you consider. Similarly, I am not taking up this. Similarly, okay, it is N is 3. It will be 3N is 9. 9. Then you have actually 3. If it is, okay, there is trouble. There is a trouble means linear molecule, non-linear molecule. Suppose non-linear, then it will be for non-linear molecule like, which is example H2O. You know H2O is a non-linear molecule. You know there is a bond angle. We call H2O or H2S. This is how many? 9. How will you distribute 9? Tell me. Yeah, H2O for non-linear molecules. What is this? 3 translation. That means cannot exceed 3. Translation cannot exceed 3. X direction, Y direction, Z direction. No way. So 3 translation 3, then rotation, there also it can be shown 3, and vibration balance. Vibration is balance 3. So this is actually how this will occur. So very good. Next I will pick up next topic. What is this? Heat capacity. So it is all over. Heat capacity. We will come back with this internal energy values later on when we will find the heat capacity of ideal gas later on. But retain these results. Heat capacity, symbol is C. What is the definition? Definition may be useful. Heat required to raise the temperature remove this. This is distracting. This is all over actually, the first law, continued. The important points that I just wrote at the top, that is already over. Okay, in first few minutes, okay, that is. We have started talking about the first law and its general form, and then we proceeded. And we are now here. It is required to raise the temperature. Raise the temperature of a body through unit degree. Okay. So what is this? Unit degree, you know, unit degree in centigrade. Change in temperature in centigrade or Kelvin are they different? 1 degree centigrade and 1 degree Kelvin as change, remember. So 1 unit degree centigrade or Kelvin. Okay. So C is from this Q by delta T. Okay. C is, acha, let me write, okay, C is for unit degree, acha, let me write this, okay, acha, I'm writing, C is, acha, right, okay, don't have to move. So I said this is a wrong statement. What is the correct statement? Noting that, acha, why? You explain why this is correct statement. Why this happens when this is not valid but this is valid, differential is valid. Why? Because C is a function of temperature. Oh, TQDT, I'm very sorry. Oh, I'm very sorry, delta T is the temperature, this T is time, delta T. Sorry, it is wrong, it is right. It is wrong, it is right. Because C is a function of temperature. So, when it is a function of temperature, you don't use delta anymore. But this is a function of temperature. So in this delta T, there are many temperatures. Which temperature C is referring to? Again, the same old story. The velocity, if they say, okay, compare high school. Velocity, B, is what? Is it correct? Delta is by delta T, displacement, velocity, displacement, and time. Recall always, forever. Time, is it correct statement? What is correct statement? dsdt is correct. This is I am writing doubtful. This is also similar, doubtful. This is doubtful. This is true. Sometimes it is true. When v is not function of time, means constant velocity. This is okay, as good as. So because if v is function of time, means accelerating particle, okay, that is accelerating particle, or decelerating, accelerating particle, okay. So then this is correct. If it is not accelerating, uniform velocity, this is same as this, because v is not, in that case, is not function of time or displacement or position. That's one. So careful. So this is analogy, okay, or analogy. So remember this. So C is so this you always insist. Now heat capacity we consider two. We consider heat capacity at constant pressure and at constant volume. What is this? Let us see. Let me write. I am writing once more. Cp, follow me. Cp, I am writing. Cp is del Q. Just following this, del Q by O, del T. This I have to write because I am giving a constant here. The moment constant, don't write D anymore. Constant means del, partial derivative. This is the Cp, heat capacity at constant pressure. This is the definition. Now I am writing. Okay, what is the? This is C. This is uppercase. C, and this is uppercase. This is lowercase. Cp is also del Q. Difference between the lowercase c. So, what is the difference between this and this? See, you have noted he is required to raise the temperature of a body. Mass is not given, is not specified. So, if actually the total body, total number of moles are involved, then it is called, what is called? Extensive property. This is intensive property. This is for total heat capacity. As I told you, total heat capacity means this is called what? This is korish na. Ja. Total heat capacity. This is what? molar. So this is intensive. Yesterday, tomorrow, actually, day after tomorrow, you have intensive, extensive. So two ways you can express. So size is not given. If size, okay, if the total heat capacity means for n moles, how many? It is 1 mole. For how many moles then? N mole is the size. This is the body, n moles. Heat required to raise the temperature of this body through unit degree, n moles of this body. And then if I consider 1 mole of this, then heat requirement will be less. So that will be, okay, expression same but result is less. What is this? What is the relation? Tell me, how much less? Capital Cp will be n times. This will be n times more or n times less. This will n times less. This I told you when I introduced extensive and intensive. So this part you have to be careful. Now given this, now for note, for gases we have two heat capacities. We have two heat capacities. As I have already mentioned, what are they? What are they? Tell me. Okay, analogy, remove this. What are they? Tell me. Tell me. Okay. Tell me. Okay. Constant pressure, heat capacity, molar or total, whatever. Another is constant volume heat capacity. But for liquids, solids and liquids, particularly solids how you consider? Solid. Oh, for gases, gases are right here. And also liquids. Though liquid is not, do this. Okay. Very good. For solids, only one. For solids, is it possible? Constant volume heat capacity is possible. That is solid. Constant volume heat capacity. Heat I am giving to a solid. How can it be volume be kept constant? How can we make the volume constant? If you give heat, it will expand. Gas will expand, but gas expand. That is volume. These are fluids. They take the shape of the container. But this you cannot have a container for this. For gas, liquid and solids require container. So gas, for example, you can force that volume to be constant and increasing the temperature. So volume constant, then what will happen? Of course, pressure will increase. So pressure will be change, keeping volume constant, possible. Constant volume heating, possible. Gas, no problem. Similarly, constant pressure is possible, as I already explained. Then volume will increase. That is very common. Constant pressure is always easy. Constant volume for gas is easy because the heat it is contained in a container. It takes the volume of the container and that is fixed. Of course, there is actually okay. See this. For solids, if you heat it will always expand. So constant volume difficult. Constant volume heat capacity to conceive constant heat capacity difficult if not impossible. Not impossible. The moment heat is added, volume will change, and we can actually contain it in a container. Say if you keep in a container, then it will not occupy the whole volume of the container. What is the whole? Gas will occupy whole entire. This room gas is occupying everything. You say this will contain. No. You always actually, so it will expand how? The interatomic distance increases. Expansion of solid. Interatomic distance increases due to heat. Interatomic spacing increases. So no one can stop. Volume increases. Constant volume difficult, impossible. So constant pressure will be, of course. So then constant pressure is okay. Heat capacity is measurable. Now question is, sir, but how to get CV of solids? Then how to get, how to find CV of solids, sir? CV of solids. How to find? I give you the solution. You know, there is a nice relation. Cp minus Cv, use this relation. Use this relation. What is the relation? Cp you can measure. Cp measurable. Cp is, remember, constant pressure is measurable. Cp we measure is what? Tv alpha square by beta. T is the temperature, V is the volume. As you see, alpha is the coefficient of, beta is the isothermal compressibility. Beta is isothermal compressibility. I'll take up this problem, and this is isobaric expansivity. Easy, very easy. This is what? Effect of temperature on volume, alpha. You know linear expansion, coefficient of expansion, linear and surface and volume. So volume, isobaric expansivity, coefficient of expansion or temperature. This is isothermal. This is compressibility means pressure volume. This temperature volume, pressure volume. Anyway, this relation will deduce. We will deduce this relation. Derive this relation after the second law started. After the second law. So see, importance of second law, imagine. With the help of the second law, you will derive this. So now one problem is solved. The second law, with the help of second law, main thing about the second law is what? Whether it is a spontaneous process or impossible process, etc. Whether reaction will occur or not. But this is additional thing that we get from the second law. This relation, this you will see, we derive in the class. You will derive. Maybe you will answer in the examination. You have to derive this equation. So Tb alpha square by beta. Anyway, so Cp measured, get out the Cv using this relation. These are measurable quantities. These are all measurable quantities. Okay, fine. Cp. Now next is what? Heat capacity, enthalpy, a new state function. H. This is the topic now. Next topic, enthalpy. Moving on. It is actually still the first law of thermodynamics and its associated things. First law. We are in the first law. When first law will be over, I'll let you know. Then we'll start second law. The second law. Maybe 10-15 classes. So enthalpy. What is this enthalpy? I tell you what. I will not give you what enthalpy is, but I will show you how enthalpy is evolved. You will better appreciate. If I give you what is enthalpy, then no. See, follow something I am doing. Consider a constant pressure process. I am running out of chalks. Constant, right. I should have brought another one. Anyway, it will do. This okay. There enough. Constant pressure process. Happy? Constant pressure process. Happy, very good. Constant pressure process, very good. Apply the first law. Constant pressure, you have, see, gas is constant pressure process, expanded acceleration. Is okay? How many minutes? Okay. So that's still running, okay, Okay. So apply the first law. What is this? dq is du fresh du plus dw. Remember dw, and if you consider dw mechanical, happy, considering no non-mechanical work. You know, the surface work, electrochemical work, there is no question. Okay, we are considering a gas expanding. So now how will you apply this? Tell me. One thing I teach you, what is the dw mechanical? Is I have told you, I have not mentioned reversible, irreversible, but you should note that it is always PdV. It is a constant pressure process. Remember. I gave you an outline there. Is actually same work. Reversible, irreversible, same in constant pressure. So that's why PdV both. If it is reversible to PdV, the irreversible also PdV. Means all PdV. Since constant pressure. So for constant pressure and constant volume, PdV. Not for isothermal and adiabatic. And constant volume, then it is zero. Both zero. So okay, note this. Noting for constant pressure process, dw mechanical is PdV irrespective of reversible or irreversible process. Okay, good, very good. So what is this then? Can I write du plus dpv? Math is du plus pv. So what you see, this u plus pv is a term, the combination of terms. So that its change is equal to heat interaction. Its change in this function, I don't know what it is, a new function, we are still wondering what it is. U plus Pv is such a function, its change is equal to heat interaction, a very important thing. Heat interaction is very important property, okay, data. So this must be very important. What is this? Whatever it is, given name. Since we will not carry u plus Pv all the time. U plus Pv, u plus y. This is so important. Give a new name. Call it H. Now at this juncture you should call it H. Instead of initially, okay, call this function u plus Pv. Call this function u plus Pv. H. Call this function u plus Pv H. Okay. So what it is? That is, you can write this dq at constant pressure note when it is valid, any condition I applied, outside this whatever written here, outside whatever written here, any condition you can write here in bracket, no non-mechanical work. System. Example, sir, when gas is expanding, why is the work, sir, non-mechanical? Why is the surface work, what is the electrochemical work, sir? Or simply chemical reaction occurring. Metal plus oxygen is metal oxide. What is the surface? So in this case, dq. Okay, so I write once more, involving no non-mechanical work. As I told you, it is not uncommon to have non-mechanical work absent. Happy? Call this function dq. Now I tell you what. So this is for finite changes. What you write? This is for differential, you see, infinitesimal small changes. For finite changes, what you write? Tell me. For finite changes, how you write this? What happens? dq integration. Finite means integration. The integration. What is the integration on right hand side? dh 1 to 2 process. So delta h. A moment ago I showed you first law itself. First law itself, infinitesimal change, finite change. Differential form, integrate. This is integrated form. If you integrate, dh is delta h, 1 to 2. And this is left hand side. Result. Good. That it is very striking. That sorry. And then what it is? If you don't want to be sorry, that is delta q. That is banned. That is forbidden. Never ever. Then you have to cut off your term. If you say delta q or q2 minus, there is no such thing as q1. Heat at a state. Don't assign heat at a state. It is not a state function. And so what you write is this delta q we can write. So I have already said this delta q don't write. We write q itself. Means delta q. Means the process. Q involved in the process. As the system moves from 1 to 2, q is associated. Remember this. I mean number of times I am repeating. So it is helpful for you. Okay, q is delta h. Okay. Now complete this. Now this side. Now if the system involves from this point, complete this. Now if the system involves non-mechanical work, if the system involves non-mechanical work, then what will you do? dw prime, what is the general form? dw prime, how do you write this? If the system involves non-mechanical work, how do you write? Tell me again, repeat. dq is du plus dw mechanical, tell me, plus first law. This is a prime is non-mechanical, okay? It is non-mechanical. I will not write all the time. I give prime means non-mechanical. So what is this? Du mechanical is what? Keep first constant pressure. Right here or dq constant pressure. You write here also. dq under constant pressure. I have already mentioned here. So if you don't mention, you write here also at the end. So here dq pressure. Okay. What is this? dw mechanical. dw mechanical is what? Yeah, this one. This one how much? dw mechanical. No. What is this? Why? Why? Answer. Yes. Answer correct. Justification. Reversible. It is normally true for reversible. dw reversible. But for constant pressure, there is no difference. So constant pressure not only, constant volume also. Constant volume both are 0. So no difference. Anyway, correct. Happy? I am happy, very happy. PdB plus dw prime. What is this? Tell me. Same way. Repeat. du plus pv plus dw prime. Remove all these things. Is what? dh plus dw prime. dq. You write here or you write here. This is the general form then. This is the general form. This is the special form. Special. In general, if it is, yes, sometimes it is involved, sir. Electrochemical work is involved. So then this is not same. So general form. General form of the relation between, tell me, between dq and dh. General form. Sure. Okay. When dw, whose class next? Okay. Anyway. dw prime is 0. If it is 0, returns. Quick. Okay. Now another thing. So what is h? Then what is H? Now get back. Achha, I'll stop in 5 minutes. Is okay? Yeah. Now what is H, sir? So start. Now again, okay? H. Next. H is what, sir? Q plus PV. Happy? Q plus PV. So absolute, not as a change. Absolute H are what? Enthalpy is what, sir? U plus PV. U is what? Internal energy. We have understanding about internal energy. We have completed internal energy. Kinetic and potential internal of constituent particles. So this is the body. And we are interested to find the H of this. H of this. What is this? Answer? Sir, H is U of this. If it is knowable, for ideal gas it is easy, that's why we took up 3 by 2, etc., 3 by 2 kT. But it is difficult though, but it is knowable. We know internal energy, what is kinetic plus potential of the constituent particles. Plus PV energy. What is the PV, sir? The pressure it is exposed to, that is 1 atmosphere. The volume is, suppose it is cylinder pi r square H. So H. Okay, H is U plus PV. This is one thing that I wanted to tell you. This is the physical significance of H. This. Another physical significance is what? This is the physical significance. This. What is the physical significance? You may write this way. Acha, I am writing from this. Yeah, I write it. Physical significance is what? Physical easy way. Physical significance of H. What? Physical significance of H is what? Here, tell me. The change in enthalpy is equals to the change. This or this change is equal to heat interaction between system and surrounding. The change in enthalpy is such a function that its change is equal to the heat interaction. If the process is constant pressure process and no non-mechanical. The change in enthalpy is equal to the heat interaction between system and surrounding implied. I am not writing. When the system involves no non-mechanical work. Write this, no non-mechanical work. When the system involves no non-mechanical work. Give a simple example of non-mechanical work. System not in, yes, Sukollam. Give a simple example of a system not involving non-mechanical work. Like say chemical work or electrochemical work or surface work. Simple example. Expansion of a gas, sir? Do it. Not any chemical reaction, sir, or in a beaker. In a beaker you are carrying a chemical reaction. So why is this, sir? No surface. So happy? Not difficult. Okay, this is. Now question is, so this is the physical significance. So physical significance of enthalpy two ways. One is as a change, heat interaction, or directly, sir, U energy plus PV energy. This is energy, this is energy, this is. So H is also, right? See, this is state function, right? State function. These are state functions. So H is also a state function. Thank you. This much. I have actually more to say on this. I'll stop here. Sorry. H is. I could not get. Good. So H is also a state function. Important outcome. H is a new state function is introduced today. H. Thank you very much with this. So we'll stop now. We'll pick up next class and we'll discuss further on this heat capacity and other things.